Space and Science News. With James. What if everything we've been told about the universe's expansion is a cosmic illusion? For decades, scientists have clung to the idea of dark energy, an invisible force said to be tearing the cosmos apart at an ever-accelerating rate. It's a cornerstone of modern cosmology, the glue that holds our understanding of the universe together. But what if that glue is cracking under the weight of new evidence? Today, we're delving into a theory so provocative it could upend everything we know about the cosmos. A group of scientists has dared to ask the unthinkable: what if dark energy doesn't exist at all? Their groundbreaking research challenges not only the idea of a smooth, ever-expanding universe but also our very perception of time itself. These researchers argue that the universe isn't expanding uniformly like a balloon. Instead, it's lumpy, filled with vast cosmic voids and intricate webs of galaxy clusters. And the acceleration we think we see. It could be an illusion, a trick of time stretching differently depending on where you look. Imagine a clock ticking faster in empty voids and slower in dense galaxies. Could this distortion be the key to unraveling one of science's greatest mysteries? But if dark energy is an illusion, what does that mean for the future of the universe? Could the timescape model, a bold alternative to the standard cosmological theory, finally provide answers to questions we've been chasing for a century? Or does it open an even deeper rabbit hole of mysteries? This journey through space, time, and the very fabric of reality is just getting started. Could the universe we thought we knew be hiding a truth even stranger than dark energy itself? For nearly a century, the expansion of the universe has been one of the greatest puzzles in science. In the early 20th century, the prevailing belief was that the cosmos was static, unchanging, and eternal. That assumption was shattered with Edwin Hubble's groundbreaking discovery that galaxies are drifting apart, revealing that the universe is expanding. Yet the plot thickened in the late 1990s, when astronomers observed that this expansion wasn't just continuing, it was accelerating. To account for this bewildering acceleration, physicists introduced the idea of dark energy, a mysterious, invisible force believed to make up roughly two-thirds of the universe's total energy. For decades, dark energy has been a cornerstone of cosmological models, helping scientists explain phenomena that otherwise defy understanding. But despite its central role in our comprehension of the cosmos, dark energy has always been a placeholder, an unknown variable plugged into equations to make the math work. No one has ever directly observed it, and its existence has remained a subject of intense debate. Critics have long questioned whether this anti-gravity force was a necessary part of the story, or simply a convenient fiction to fill gaps in our knowledge. Now, a team of physicists and astronomers at the University of Canterbury in Christchurch, New Zealand, has shaken the foundations of this narrative. Their research, published in the prestigious monthly notices of the Royal Astronomical Society Letters, suggests that dark energy may not exist at all. Instead, they propose a radical new idea, that the universe isn't expanding uniformly, as previously assumed, but in a more varied and lumpier fashion. This uneven expansion, they argue, could be a result of the intricate web of cosmic structures, clusters of galaxies, sprawling filaments, and vast, empty voids that shape the fabric of space itself. Could this bold theory rewrite the story of cosmic expansion? If dark energy is merely an illusion born from oversimplified assumptions, what other surprises might the universe be hiding? The mystery, it seems, has only deepened. At the core of this provocative new research lies the timescape model of cosmic expansion, a bold alternative to the conventional dark energy paradigm. Rather than relying on an invisible force to explain why the universe appears to be expanding at an accelerating rate, the timescape model shifts the focus to the way we perceive time and distance. It suggests that the apparent acceleration is not a true feature of the cosmos but rather a result of how we measure and interpret the universe's expansion. The model builds on a fundamental aspect of general relativity, the relationship between gravity and time. Gravity, according to Einstein's theory, can warp the fabric of spacetime, slowing down clocks in regions of strong gravitational pull. In the context of the timescape model, this means that an ideal clock ticking in the emptiness of a cosmic void, regions of space nearly devoid of matter, would run faster than a clock located within the dense gravitational environment of a galaxy. The researchers behind this theory propose that this time dilation effect is far more significant than previously acknowledged. For instance, a clock in the Milky Way galaxy would tick approximately 35% slower than a clock in a large cosmic void. Over billions of years, this disparity in the passage of time has profound implications. In the voids, where time has flowed faster, the universe has had more time to expand, leading to the perception of an accelerating cosmos when viewed from our galactic vantage point. Professor David Wiltshire, who spearheaded the study, puts it succinctly: our findings show that we do not need dark energy to explain why the universe appears to expand at an accelerating rate. Dark energy is a misinterpretation of the variations in the kinetic energy of expansion, which is far from uniform in a universe as lumpy as the one we inhabit. This revelation challenges the very foundation of cosmology. By eliminating the need for dark energy, the timescape model forces us to reconsider how we interpret the interplay of gravity, time, and space. If this theory holds true, it could redefine our understanding of the universe and its evolution, raising as many questions as it answers. Is it possible that the cosmos we observe is an intricate illusion shaped by our position within it? Or are we only beginning to scratch the surface of a deeper, more complex truth about the fabric of reality? For decades, the lambda cold dark matter, lambda CDM, model has served as the cornerstone of modern cosmology, offering a framework to explain the universe's accelerating expansion through the mysterious presence of dark energy. This theory largely emerged from observations of distant supernova explosions, whose light revealed that these cosmic events were farther away than expected, implying an accelerating expansion. Yet, cracks in this seemingly solid foundation are beginning to show. One of the most significant challenges to the lambda CDM model arises from the Hubble tension. This discrepancy refers to the mismatch between measurements of the early universe's expansion, as captured in the cosmic microwave background, CMB, and the current expansion rate observed today. The CMB, an ancient glow left over from the Big Bang, offers a snapshot of the universe when it was just 380,000 years old. Calculations based on this data predict a slower expansion rate than what we observe today, leaving cosmologists puzzled. Adding to the mystery, the Dark Energy Spectroscopic Instrument, DESI, a cutting-edge project that maps the large-scale structure of the universe, has produced new, high-precision data that complicates the picture even further. This data suggests that the lambda CDM model struggles to align with observations unless dark energy is assumed to evolve over time, rather than remaining a constant, unchanging force as the model originally proposed. At the root of this problem is a century-old equation, Friedmann's equation. This mathematical description of cosmic expansion assumes that the universe, on large scales, is homogeneous and isotropic, essentially, a smooth, featureless soup of matter and energy. But the universe we observe is anything but uniform. Instead, it forms a vast cosmic web, with dense clusters of galaxies connected by filaments of matter and separated by immense voids. These intricate structures complicate the simplistic assumptions of the lambda CDM model, raising questions about whether Friedmann's equation can accurately describe such a lumpy cosmos. These growing anomalies have opened the door for alternative theories, such as the timescape model, to challenge the status quo. Could the lambda CDM model's reliance on dark energy be an oversimplification of a much more complex cosmic reality? If so, what does that mean for the future of cosmology? The deeper scientists delve into these discrepancies, the clearer it becomes that the universe may not conform to the neat, tidy picture we've painted over the last century. Instead, it could be hiding layers of complexity we are only beginning to unravel. The quest to unravel the mysteries of cosmic expansion has reached an exciting new phase. Researchers at the University of Canterbury have joined forces with the Pantheon Plus collaboration, analyzing an unprecedented dataset of 1,535 supernovae. These exploding stars, scattered across the cosmos, act as cosmic lighthouses, enabling astronomers to measure the universe's expansion with remarkable precision. Intriguingly, this new data lends substantial support to the timescape model, offering a possible resolution to the persistent Hubble tension and other anomalies that have baffled cosmologists for years. But the journey to validate this alternative theory has only just begun. The European Space Agency's Euclid satellite, launched in July 2023, is poised to play a pivotal role in this endeavor. Armed with cutting-edge instruments, Euclid is designed to map the large-scale structure of the universe and examine its expansion history in unprecedented detail. Crucially, it has the capability to test the predictions of the timescape model against those of the traditional Friedmann equation. To do so, however, it will need to gather data from at least 1,000 independent high-quality supernovae, a challenging but achievable goal given Euclid's advanced technology. Adding to the excitement is the upcoming contribution from the Nancy Grace Roman Space Telescope. Scheduled for launch in the near future, this observatory promises to expand the pool of high-precision data, further illuminating the nature of the cosmos. By combining observations from Euclid and the Roman telescope, scientists aim to refine their understanding of cosmic expansion and potentially confirm or refute the timescape model. Professor David Wiltshire, who has been at the forefront of this research, is optimistic about the road ahead. He believes that the abundance of data from these new missions could finally bring clarity to one of cosmology's most enduring puzzles. We now have so much data that, in the 21st century, we can finally answer the question, how and why does a simple average expansion law emerge from complexity? Wiltshire explains. He emphasizes that while Einstein's general relativity remains foundational, the simplistic assumptions underlying Friedmann's equation may no longer hold up in the face of a lumpy and dynamic universe. The implications of this research are staggering. If the timescape model continues to gain traction, it could signal a paradigm shift in cosmology, overturning decades of reliance on the concept of dark energy. As the Euclid and Roman missions progress, scientists anticipate that the coming years will bring us closer than ever to solving the universe's most perplexing mystery. Could this be the dawn of a new era in our understanding of the cosmos? Only time, and the data, will tell. The potential implications of this research could reshape the very foundation of modern cosmology. If the timescape model holds true, it challenges one of the most significant concepts in astrophysics, dark energy. For decades, dark energy has been the cornerstone of our understanding of the universe's accelerating expansion. Yet, this new perspective suggests that what we've interpreted as a mysterious force might actually be an illusion created by the intricate, uneven structure of the cosmos. The timescape model invites us to see the universe not as a uniform expanse, but as a patchwork of dense clusters, vast voids, and twisting filaments. By recognizing the complexity of this cosmic web, we can address some of the most pressing controversies in cosmology, such as the Hubble tension, a glaring discrepancy in measurements of the universe's expansion rate, and puzzling data from DESI that seem to defy traditional models. If the timescape model is correct, it could also open doors to solving problems that have lingered for decades, offering a more nuanced and accurate depiction of cosmic evolution. As we step into the era of precision cosmology, instruments like the Euclid satellite and the Nancy Grace Roman Space Telescope will be critical in testing these bold ideas. By capturing data on the largest scales with unparalleled detail, these tools will help scientists refine their measurements of cosmic expansion and further probe the validity of the timescape model. Over the next decade, this wealth of new information might allow researchers to definitively settle the debate over whether dark energy is a genuine force or simply a misinterpretation of cosmic complexity. This research also underscores the value of questioning long-standing assumptions. The history of science has shown time and again that challenging established models can lead to breakthroughs that reshape our understanding of reality. Whether the timescape model is ultimately proven or refuted, its development has already expanded the boundaries of our thinking about the universe. As the race to uncover the truth about cosmic expansion accelerates, one thing becomes increasingly clear: the universe is far more intricate and enigmatic than we ever imagined. Each new discovery brings us closer to answering the age-old question of how our cosmos truly works. But even as we solve one mystery, countless others await, reminding us that the pursuit of knowledge is endless, and that the greatest revelations may still lie ahead. The quest to understand our universe's expansion continues to captivate scientists and stargazers alike. The timescape model presents a bold challenge to the long-held concept of dark energy, offering a fresh perspective on cosmic evolution. By considering the lumpy nature of our universe and the effects of gravity on time itself, this new theory could revolutionize our understanding of the cosmos. As we've explored in this video, the implications of this research are far-reaching. From resolving the Hubble tension to explaining anomalies in cosmic expansion, the timescape model offers potential solutions to some of cosmology's most perplexing puzzles. The next decade promises to be an exciting time for astronomers and physicists as new data from advanced space telescopes like Euclid and the Nancy Grace Roman Space Telescope pour in. This cutting-edge research reminds us that science is a dynamic, ever-evolving process. Today's accepted theories may be tomorrow's discarded notions, replaced by more refined and accurate models. The story of dark energy, or perhaps its absence, is far from over, and we're privileged to witness this scientific journey unfold. Thank you for joining us on this cosmic exploration. If you enjoyed this video and want to stay updated on the latest developments in astronomy and cosmology, don't forget to subscribe to our channel. Hit that notification bell to ensure you never miss an upload. Your support helps us continue bringing you fascinating content about the wonders of our universe. Until next time, keep looking up and questioning the cosmos. Thanks for watching. Remember to like, subscribe, comment, share and click that notification bell so you never miss out. See you next week.